urgent but steady. Operating heavy machinery in extreme environments carries a constant physical risk. A sudden rollover or a violent rockfall can trap an operator in an instant, and their survival depends entirely on the metal structure surrounding them. To guarantee that protection, equipment must be pushed to its breaking point in a controlled setting. Today, we will walk through the exact steps required to pass the rigorous ISO 3471 and ISO 3449 safety certification tests. Before you schedule lab time, you must secure two prerequisites: a finalized structural canopy design and the exact gross vehicle weight, or GVW, of your machine. Methodical. Executing these tests in the correct standardized sequence is the only way a manufacturer can mathematically prove that a raw metal cage will function as a life-saving survival cell. Before any physical metal is destroyed, your canopy design must first be evaluated in a virtual environment. This diagram shows a finite element analysis. Running CAD simulations generates a heat map visualizing how pressure distributes across the roof and pillars. Identifying weak points allows you to reinforce the geometry now, preventing expensive structural failure during physical trials. Once the digital design is optimized, we move to the testing lab. A prototype of the substructure is fabricated and securely mounted to a test bed. This schematic illustrates the deflection limiting volume, or DLV, the physical space occupied by a 95th percentile operator. The rule is absolute. Under stress, the canopy can bend, but if the metal breaches this DLV space at any time, the design fails. The core engineering challenge is not building a perfectly rigid box. It is managing structural deformation so the kinetic energy safely diverts around the operator. The first physical trial is the FOPS test, Falling Object Protective Structures, dictated by the ISO 3449 standard. Machines fall into Level 1 or Level 2 requirements based on their operating environment. Level 1 covers lower-risk applications like highway maintenance, while Level 2 is mandatory for heavy forestry and mining. This schematic details the parameters required to pass a Level 1 test. Notice the 45-kilogram round test object dropped from 3.1 meters. For a Level 2 test, the scale increases aggressively, requiring a 227-kilogram steel cylinder dropped from 5.2 meters, generating 11,600 joules. During the physical execution, the object is released into freefall, smashing violently into the center of the reinforced metal roof panel. Immediately following the dynamic impact, lab technicians measure the deformation to verify if the crushed roof breached the DLV envelope inside the cab. Passing this stage triggers the sequential trap rule. You are forbidden from repairing or reinforcing the damaged frame. This rule guarantees that the upcoming rollover test evaluates the cabin in its most degraded, pre-stress state. It perfectly mimics a multi-directional disaster where a machine is struck by falling debris just before rolling down an embankment. Still bearing the damage from the drop test, the canopy moves to the test bench for rollover protective structures, or ROPS, under ISO 3471. The target testing forces applied here are calculated precisely based on the machine's gross vehicle weight. A heavier machine requires exponentially more structural resistance. This schematic outlines the ROPS bench setup, a strict three-part static sequence. Phase 1 applies a horizontal lateral load, simulating a tipping machine. Phase 2 applies a vertical load, simulating upside-down weight. Phase 3 applies a longitudinal load, stressing joints to their limit. The physical reality of this sequence involves immense slow pressure. The rams push against the steel until it begins buckling, maintaining target force without snapping. Passing this final static stage means the crushed frame has successfully absorbed the required energy while keeping the operator's DLV completely untouched. By surviving the dynamic drop and the three-stage static crush in order, the engineering mathematically proves the structure can save a human life when momentum overwhelms the operator. With the physical destruction finished, we transition to the post-test reporting phase. The lab compiles all raw force measurements and deflection metrics. A professional engineer must review this exact data and officially stamp the structural test report, verifying the math and legally confirming the results. That stamp earns you the final reward, a permanent OEM safety certification label, which must be physically riveted to the machinery frame before deployment. To reach this milestone, Finalize your CAD files and contact an ISO 17025 accredited testing lab. You now have the roadmap required to turn your blueprints into a verified, field-ready machine.